Deep inside the world's most advanced data centers, a quiet but profound crisis is unfolding. The artificial intelligence models driving today's technological revolution are extraordinarily powerful, but they are also incredibly inefficient. A massive server farm running a large language model consumes enough electricity to power a small city, requiring millions of dollars in cooling infrastructure just to keep the silicon from melting. Yet the human brain, capable of far more complex reasoning, creativity, and real-time adaptation, operates on roughly 20 watts of power. That is less energy than a standard incandescent light bulb. This staggering disparity between biological efficiency and synthetic brute force is not just a scientific curiosity. It is the central hardware engineering challenge of our time. The root of this massive energy consumption lies in a design paradigm that has dominated technology since the 1940s. Almost every computer, smartphone, and AI server on the planet relies on the von Neumann architecture. In this traditional setup, the processing unit and the memory unit are physically separated on the motherboard. Every single time the system needs to perform a calculation, it must fetch data from the memory bank, pull it across a microscopic highway to the processor, compute the result, and then send it all the way back. Engineers refer to this constant shuttling of information as the von Neumann bottleneck. When running complex AI algorithms that require processing billions of parameters simultaneously, this bottleneck becomes a massive drain on both speed and power. The processors spend a vast amount of time and energy simply waiting for data to arrive. Traditional computing attempts to brute force its way through this traffic jam by pumping in more electricity and building faster, hotter data pipelines. But physics dictates that we cannot shrink transistors or pump power into silicon indefinitely without hitting a thermal wall. To build the next generation of artificial intelligence, researchers are abandoning the traditional computing playbook entirely. The solution is not to build a faster calculator, but to engineer hardware that directly mimics the structure and function of the human brain. This rapidly advancing field is known as neuromorphic computing. It is a radical reimagining of silicon, designed from the atomic level up to process information exactly like biological neural tissue, prioritizing extreme energy efficiency over raw sequential speed. In a neuromorphic chip, the strict division between memory and processing is completely erased. Instead of a centralized processor fetching data from a separate memory bank, these chips use artificial neurons and synapses that compute and store information in the exact same physical location. This decentralized architecture eliminates the von Neumann bottleneck entirely. Information does not travel across a motherboard. It stays highly localized, processed instantly by the specific artificial synapse that holds the memory, mirroring the dense, interconnected web of the human cortex. This localized processing is powered by a biological concept translated into silicon, known as spiking neural networks. Traditional AI models operate continuously, constantly calculating numbers and draining power even when the input data has not changed. Biological brains do not work this way. Human neurons only fire or spike when they receive a strong enough stimulus from their environment. If there is no new information, the neuron remains silent and consumes virtually zero energy. Spiking neural networks replicate this exact event-driven processing. The push to commercialize this event-driven architecture has led to remarkable breakthroughs from major technology pioneers. IBM took a massive leap forward in this space with the creation of TrueNorth. This pioneering neuromorphic chip was designed to process complex, continuous sensory data, like recognizing objects in a live video feed, but with a fraction of the power required by a standard graphics processing unit. TrueNorth features over 1 million programmable neurons and 256 million programmable synapses, all operating in massive parallel coordination. The results from the TrueNorth project fundamentally shifted industry expectations regarding what low-power silicon could achieve. Because its artificial neurons only use power when they actively spike, the chip operates on mere milliwatts of electricity. It proved definitively that highly complex pattern recognition could be achieved without the massive thermal footprint of traditional data centers. The energy savings were not just incremental improvements of 10 or 20%. They were orders of magnitude more efficient, proving that brain-inspired AI could function effectively outside of massive temperature-controlled server farms. Building on these foundational proofs of concept, Intel introduced its own highly advanced neuromorphic research chip, known as Loihi. While earlier designs proved the extreme energy efficiency of spiking neural networks, Loihi added a crucial new capability to the hardware: real-time learning. Traditional AI models require a distinct, highly intensive training phase before they can be deployed to make predictions. If a traditional model needs to learn to recognize a new object, the entire network often has to be retrained from scratch on massive cloud server clusters. Loihi changes this dynamic entirely by allowing the artificial synapses to adapt and rewire themselves on the fly, directly on the silicon. This mimics the concept of neuroplasticity in the human brain. When exposed to new stimuli, the chip can learn to recognize a new odor, a new gesture, or a new visual pattern instantly, without ever connecting to a cloud server or requiring a software update. This on-chip learning capability represents a massive paradigm shift for autonomous systems operating in unpredictable, rapidly changing environments. The applications for this technology naturally gravitate toward systems that require constant vigilance but have strictly limited power supplies. Neuromorphic chips excel at processing time series data from dynamic vision sensors. Unlike standard cameras that capture full frames of pixels 60 times a second, dynamic vision sensors only record changes in lighting or movement. When paired with a spiking neural network, this creates an artificial visual system that operates exactly like a biological eye, ignoring static backgrounds and only processing actual movement, saving immense amounts of computing power. The implications for real-world technology are profound. Neuromorphic computing unlocks the true potential of edge AI, moving advanced artificial intelligence out of the centralized cloud and directly into our personal devices. Imagine medical implants that monitor heart rhythms continuously, instantly detecting anomalies and learning a patient's unique baseline without needing a Wi-Fi connection. Consider search and rescue drones that can navigate collapsed buildings, learning to recognize survivors in real time, powered entirely by a battery no larger than a coin. This shift to edge computing also fundamentally rewrites the rules of global data privacy. Currently, smart home devices, voice assistants, and security cameras must constantly stream audio and video to centralized corporate servers for processing, creating significant security vulnerabilities. Brain-inspired AI chips can process that complex sensory data locally on the device itself. The voice recognition or facial analysis happens entirely within the hardware, meaning your highly personal biometric data never has to leave your home or traverse the public internet. Despite these massive advantages, the transition to neuromorphic computing is not a simple hardware upgrade. It requires completely dismantling decades of software engineering. Every major programming language, operating system, and software application in existence was built specifically for the von Neumann architecture. You cannot simply take a modern large language model, coded in standard programming languages, and run it on a spiking neural network. The fundamental mathematics of traditional software do not align with the asynchronous, event-driven nature of biological hardware. Engineers are now forced to invent entirely new algorithms, compilers, and programming frameworks from scratch. They are essentially trying to write software that mimics organic biology rather than rigid logic gates. This involves complex physics, specifically utilizing microscopic components like memristors. A memristor is a unique electrical component that remembers the exact amount of current that has previously flowed through it, even when the power is turned off. This analog property makes it the perfect building block for an artificial synapse, but controlling millions of them requires a completely new branch of computer science. The current software gap means that neuromorphic chips will not replace traditional processors overnight. Instead, the immediate future points toward a highly specialized hybrid architecture. Standard silicon processors will continue to handle sequential logic, operating systems, and traditional software applications. Meanwhile, neuromorphic coprocessors will be integrated into the exact same motherboards to serve as dedicated sensory engines, handling visual processing, pattern recognition, and real-time adaptation with zero latency. This hybrid approach is already beginning to take shape in automotive and aerospace engineering. Autonomous vehicles require the processing of massive amounts of radar and visual data in milliseconds to navigate safely, Traditional computers struggle to process all these simultaneous, continuous inputs without drawing massive amounts of battery power and generating excessive heat. Brain-inspired coprocessors can filter this sensory noise efficiently, only waking up the main vehicle computer when a critical event, like a pedestrian stepping into the road, actually occurs. Ultimately, the pursuit of this technology is not just about building smarter gadgets or faster drones. It is about the physical sustainability of artificial intelligence itself. As global demand for generative AI continues to explode, the international energy grid is being pushed to its absolute limits. The current trajectory of building endlessly larger, power-hungry data centers is ecologically and economically unsustainable. We cannot achieve true artificial general intelligence if the hardware requires a dedicated power plant to function. The quest for brain-inspired AI represents a full-circle moment in the history of technology. For decades, we tried to teach silicon to think by forcing it to calculate faster and faster, ignoring the immense energy cost. Now, we are realizing that nature already solved the problem of intelligent, highly efficient processing millions of years ago. By bridging the gap between biological elegance and synthetic hardware, we are not just solving a computing bottleneck, we are laying the physical foundation for the next true leap in artificial intelligence.